Well, good morning, everyone, and welcome to cup number 4 of Cosmic Coffee, coming to you live this Thursday morning from our campus here on Mars Hill and out in Flagstaff. This is one of our programs that we've started to help stay in touch with everybody during the era of isolation and lockdowns. And thank you for joining us this morning. Each week we try to give a shout out to one of our struggling local businesses, and we're shouting out this morning to the Cedar House Coffee Shop over there on Cedar Avenue across from the Safeway near Coconino High School. They have curbside pickup, so consider supporting our businesses to the extent you can during these rather unusual times. Now, every week on Cosmic Coffee we feature a different topic. And so this week, we're joining the celebration of the 30th anniversary of the Hubble Space Telescope, one of NASA's great observatories and a facility that has not only advanced our understanding of the universe in so many ways, but also provided some of the most incredible, memorable images of the cosmos. Lowell Observatory astronomers have made extensive use of the Hubble Space Telescope over the years. And joining us this morning is one of them, Dr. Deidre Hunter of our faculty, who's here to talk a little bit about the telescope and just one of the many different types of projects that we've done with it to advance our understanding of the universe. So welcome, Deidre. It's great to have you here.
Thank you.
So we're going to start by talking a little bit about this incredible observatory itself. Despite a 30-year legacy and an incredible variety of science, there were quite a few growing pains associated with getting Hubble to the level of performance we've been seeing, weren't there?
Yes. First of all, there were the usual delays in any space telescope project. I think it was supposed to be launched in 1983, and that got delayed to 1986. And in January of that year, unfortunately, and it was supposed to be put into the space shuttle and launched, and the astronauts were going to release it. And in January of that year, one of the space shuttles, the Challenger, blew up shortly after launch. So everything got delayed. And it was 1990 before it was finally launched. And then I was on the WIFPIC team, the Wide Planetary Camera team, the first camera that flew on Space Telescope. I was one of about 30 or so people on the team. And we were supposed to help with the calibration of the filters and all sorts of support for getting the information that people needed to do science with the camera once it was launched. So when it did go up in 1990, the team had rented space at Bowie State, a little college south of Baltimore. We went there and took turns, and I wasn't present when the first image came down, but what I heard was that the first image came down and people looked at it and they said, "What in the world is going on?" And this is what they saw. This is not from the WIFPIC, it's from a different camera on the telescope, but the image on the left was what a single isolated star looked like, and on the right was what it was supposed to look like and what it eventually did look like. And people looked at these images with these humongous snowballs of stars instead of these little pinpoints of light. And the story I heard was that Roger Linz, who was one of the astronomers on our team, looked at it and he said, "Spherical aberration." And sure enough, the mirror had been misfigured and it had aberration, which scattered the light out into this huge blob rather than a tiny little pinprick. And the result was that in a very, very short 3 years, the people built a new instrument called COSTAR, which was put where the astronauts then went up again to the space telescope, captured it again, and put in this new instrument called COSTAR, which had in it optics for each of the instruments on the telescope that would undid or corrected for the aberration. And as long as they were doing that, they built a new camera, WIFPIC 2, very imaginative name. So it was WIFPIC, but now it had built into it the optics to correct for the aberration. So the astronauts put in, this shows the astronaut pulling out the old WIFPIC camera, and they put in the new one, and COSTAR, and then we got images like this, where on the left, again, this is a picture of a galaxy taken with WIFPIC, and the picture on the left is what it looked like before the correction, and then the one on the right is what it looked like after the correction. So you can see what an enormous difference it made. So it was 1993 before the telescope was at its best.
Yeah, but you said you characterized it as a very, very short 3 years, and I think we should emphasize for the viewers to build an instrument and deploy it, particularly for a space-based observatory, in 3 years is an astounding achievement.
Yeah, right.
Okay, no, go ahead.
No, that was it.
Okay, so I think the next slide was this spectacular nebula. Is that right?
Yeah.
Yeah. So this is, I think, what we call an H2 region, and so yeah, tell us a little bit about this. I think now we're getting into science that we can do with this fabulous facility.
Right. This is actually a ground-based image because the nebula is huge, and Space Telescope had a small field of view in its cameras. But so this is a giant star-forming region that is in, and what you're seeing here is all the gas and dust, the brown spots are the dust, concentrations of dust. And so it's a huge star-forming region with star formation going all on throughout it. But at the center of it, or approximately the center, there's this beautiful cluster of stars called R136. And so this object, this cluster.
Okay, point when we're live again. Okay, everyone, we took a break there just to stop and restart our stream and see if we get a slightly better handshake with YouTube. There seemed to have been a lot of delay and buffering in the last time. I think right now that was a great image you showed from space-based and ground-based comparisons of the star cluster. One thing we do sometimes hear frequently these days, well, if the images from space are so magnificent, does that sort of obviate or make ground-based facilities obsolete? And maybe that's a point we could touch on briefly here.
No, not at all. You don't always need very high spatial resolution. Maybe what you need instead is very high sensitivity if you're looking at something very faint. So Space Telescope was really a relatively small telescope. I think it was, Jeff, is it 2.5 meters?
2 meters, yeah.
In diameter, the mirror, and for example, Lowell Observatory's Discovery Telescope is 4.3 meters. And they're building telescopes today that are 30 meters and such. So if you want to observe something really faint, you might choose a ground-based telescope that's larger, or if you just don't need that spatial resolution, then there's no point in using an expensive telescope.
Right. And of course, there is, you just used the magic word, there's the expense question too, per meter of aperture, the expense to deploy something in space as opposed to build it on ground and then maintain and service it is pretty dramatic.
That's right.
Okay, so let's move on and hear a little more about R136. It sounds like we've got good audio and video now.
Okay, so this is our beautiful picture of the cluster from Space Telescope. Where we can see lots and lots of stars. And one of the reasons that it's so interesting is that it has lots and lots of stars that formed in a very small space, and we'll come back to that later. But this high spatial resolution image then gave us the ability to identify all the stars in the cluster. We observed, the WIFPIC team observed this through 3 different filters so that we could measure the brightness and color of the stars in these different filters. And then that let us plot the stars on this, what's called a color magnitude diagram. So along the x-axis is color, with bluer to the left and redder to the right. And then going up, you go up in brightness of the star. And on this diagram, then each black dot is a different star in the cluster. And so you can see this band of stars in the middle of the plot, and it's labeled main sequence. And that's where stars, once they form, they sit there with nuclear fusion going on in the core, and they're burning hydrogen. And they sit there until they run out of hydrogen in the core, and then they start to evolve redward from there. We'll come back to that later too. And so those stars are all settled and burning hydrogen. Then down below that, in the bottom third, you see stars off moving redward. They're off to the red side of the main sequence. And there's sort of a big cloud of stars down there. And that's labeled pre-main sequence. And those are stars that are still settling. They've formed enough that we see them as a star, but they aren't settled yet, and so they're settling down to the main sequence, and then up above the at the top are the massive stars. They're really bright and hot, and we'll come back to those. You can see I've labeled down at the very bottom is about 1 solar masses, around about a third of the way up, it's 2.8 solar masses. I can point to it here. This is around 2.8 solar masses, and up here is about 18 solar masses. And so we're seeing stars of all different mass ranges. Our signal to noise peters out as you go down to the bottom, and so our ability to detect the stars goes down as you go down to the bottom. And then also the fact that the stars are on 3 main sequence tracks makes it difficult to assign them masses. So for what I'm about to talk about, we confined ourselves to the intermediate mass stars, from 2.8 solar masses up to 18 solar masses. And one of the issues, one of the things that was scientifically interesting about this cluster is that people had found, people like Phil Massey and others had measured had looked at different star forming regions around the Milky Way and the Large Magellanic Cloud and other galaxies, and they found, and Saltpeter was the first person to do this, and he found that there was a certain proportion of stars, that the massive stars were rare and the low mass stars were very common and numerous, and that there was a function that described the proportions. So the number of stars is a function of the mass of the star. It's called the stellar initial mass function, and it has a certain exponent that describes how that function looks, those proportions. And so but where people had looked before had always been the more common OB associations, which are very loose associations, so stars aren't really crammed together and there aren't as many of them. And this was a more extreme star forming event, this cluster. It was lots of stars in a small space. And so people thought that this function would be different, the proportions would be different. And so what we did, so I measured the brightnesses of the stars and assigned them masses, and then measured this proportion, the function, and the slope of this function, and I found that it was normal. It was just like all the other OB associations. And for me, this was, there are some times in your career when you do something and then you just go, wow. Most of the time it's, huh?
Yeah,
You
right.
finish some project and you go, huh? What does that mean? And there are all these more questions. But in this time it was, wow. And as far as I was concerned, that was the end of the question. we had answered it. It was done. Now the controversy went on for decades, but from my point of view, the answer, we had the answer. Even in these extreme star-forming environments, the proportions were normal, and I was done with that part of it. So that was exciting, and this just shows how R136 is different. Now that we had counted the stars and we counted them and we knew what the concentration of stars was, along the x-axis is the number of stars. I call that the richness, and on the y-axis is the number of stars per unit area. I call that the concentration. So this line down here at -2. There, these objects here that my cursor is circling, that's where the OB associations in the Milky Way and the Large Magellanic Cloud sit. There are some regions, this is a star-forming region in M33, the Triangulum galaxy, and some other peculiar galaxies that have a higher richness, but they're not that much more extreme. Here sits R136 up here in terms of having lots of stars and a very high concentration.
And that y-axis is also a logarithmic scale, right?
Yes, right.
Yes, so it's really concentrated.
Yeah. And so that was very exciting. But there was another question, another issue that R136 was famous for, and was a reason also for observing this with Space Telescope. At the very center of the cluster is this object, R136a, and from ground-based images, it appeared to be a single star, but it was so luminous that it would have to be 2,000 times the mass of the sun. That's a humongous star. No other star that massive had ever been seen. And I remember papers in the literature at the time, theorists and modelers were trying to figure out how you would form such a massive star, how and why, how you would keep it stable enough so that nuclear fusion could go on in the center, and what would happen to it, how long would it live, what would happen when it exploded as a supernova. The massive stars explode as supernovae. What would happen to the star? So people were very excited, interested in the star. So with Space Telescope, the Space Telescope image, HST revealed that R136a was actually a dozen stars, wasn't a single star. So it didn't have to be so massive, but there still was the question of, well, how massive are those stars, and are they present in the normal proportions that we had seen for the intermediate mass stars? And so at this point, I joined forces with Phil Massey, who is an expert on massive stars, and this was not part of the WIFPIC team data. We had to put in a proposal to HST and ask for telescope time. And the reason is that the massive stars, you can't tell their mass from their color. I was able to use just the color and to figure out what the mass was for the intermediate mass stars, and that was good enough. But for massive stars, a 100 solar mass star and a 20 solar mass star don't follow the same color. That's because most of their light is out in the ultraviolet. And so you have to get spectra. So you have to get spectra of the stars, and then you look at the absorption and emission lines. You classify the star and you figure out their mass that way. And Phil Massey was an expert at that, but we needed these new data. We needed spectra. And this shows now the whole cluster area.
So Deidre, we do have we have one question that came in just asking for a reminder of what region of sky we're looking at when we're studying R136.
So this is in the southern hemisphere, the Large Magellanic Cloud, and the Large Magellanic Cloud, I forget exactly what its declination is, but it's like minus 60 degrees or something like that. So it's way far south.
Right. So you got to go to Chile, not visible from Flagstaff or the United States.
Right. And so we wanted spectra of about 100, what looked like there were 100 or so massive stars in the cluster, and that's a lot. And there were two things that enabled this to be efficient enough for us to be able to get the telescope time to do it. The first is that Space Telescope was pretty stable. When you wanted to take a spectrum, you had to go to a nearby isolated star, center up, the telescope, and then offset from there to your object of interest, and then take the spectrum. And if you had to do that centering before each spectrum, it would take an enormous amount of time. But in fact, it was stable enough, we were able to just center up and then take offset 1, offset 2, offset, just keep offsetting and getting spectra. So that made it more efficient. And the other thing is that R136 happens to fall in a nearly continuous viewing zone, which means that so Space Telescope's orbiting around the Earth, and every 90 minutes it goes around, and half the time it's the Earth's in the way. So you observe for about 40 or 45 minutes, and then you have to stop, wait for it to come around, and then start again, and that's very inefficient. But with this being in a continuous viewing zone, we were able to just go and just hop around getting spectra. And in the end, we got a spectra of 67 stars. And so we got the spectra, and Phil reduced the data, and he printed out the spectra like this, and he started doing his classification. He particularly was interested in the helium-2 line here, and I noticed he's marked helium-1 here, and so he was classifying the spectra, and he classified this spectrum, and it was an O3 star. O3 exclamation, exclamation, exclamation.
It's really an O3 star.
Because O3s are the hottest, most luminous type O star. O stars are the massive stars. And so an O3, wow, we found an O3 star. And then he looked at the next one, another O3. Notice his question marks beginning to appear. Another O3. And oh my goodness, another O3, what in the world is going on? So Phil goes back to look at the data to make sure there wasn't a problem with the spectra, the reduction of the spectra, and that we were actually observing different stars each time. And in fact, we found that 39 of the 67 stars were O3 type stars, the hottest, most luminous O stars. And this was about 4 times the number of all O3 stars previously known. So it was quite spectacular. There were also some stars that had had emission lines, big broad emission lines. These, which are characteristic of evolved O stars, evolved massive stars called Wolf-Rayet stars, and Phil talked about those last week. But these were unusual. they were unusual because they also had lots of hydrogen lines, and they were too bright by up to a factor of 10. So Phil concluded that they weren't Wolf-Rayet stars at all, and he called them OS stars on steroids. And an OS star is a supergiant O star. So these were spectacular. So the Wolf-Rayet stars were not, they weren't Wolf-Rayet stars, and that's important because Wolf-Rayet stars are nearly it's toward the end of the lifetime of a massive star, and set the time scale for the lifetime of the stars to be about the lifetime of the massive stars to be of order 3 million years. When Phil had determined the masses of all the stars and put them on this now a temperature versus bolometric magnitude, you see the main sequence of the massive stars. Now we're just looking at the massive stars, and these lines that go off to the red to the cooler side of the diagram, those are tracks for how a star evolves over time. So like this is the 15 solar mass track. It starts here on the main sequence, and after it runs out of hydrogen in the center, it starts to evolve off to the cooler temperatures and wanders around over here on the other side of the diagram. And so from this, we concluded that the massive stars were 1 to 2 million years old. And that means that none of the massive stars were yet old enough to have died. And when these massive stars die, they explode as supernova. And so in another 1 to 2 million years, there are going to be a lot of stars exploding as supernova in R136, and it's going to be very spectacular. I wish that I could be around.
I was going to say, I'm going to look forward to that.
It will be beautiful. But anyway, so we had an age. That was interesting. We had determined for the intermediate mass stars and the pre-main sequence, they seem to be between 4 and 6 million years old, or something like that. And so it's possible that the massive stars formed after the lower mass. And we, so then we did what we had done for the intermediate mass stars and measured the number of stars as a function of the mass of the star to see if it was consistent with the intermediate mass stars, and it was. So we found that this proportion of stars was the same as in other regions from 2.8 solar masses up to the most massive star. This plot just shows this slope for the stellar initial mass function. Here's a region in the SMC. These are star-forming regions measured in the Large Magellanic Cloud. This is the Milky Way. And here's R136 sitting there looking completely innocuous.
Right. And so you might, for our viewers, maybe clarify this simple-minded method astronomers use of defining what we call metallicity.
Ah, yes. So metallicity is the amount of atoms that are heavier than helium.
Right.
So anything heavier than helium, hydrogen and helium are not metals, and everything else is.
Right. So this is the astronomer's brain, the periodic table: hydrogen, helium, other.
Exactly.
Yep.
Right. And so the SMC is the most metal poor, the LMC is next, and the Milky Way is more metal rich.
Yeah.
Okay. And so there was one more thing that was very interesting to consider in this cluster, and that is, what was the most massive star? We found all these massive stars. What was the most massive star in the cluster? And so based on Phil's very conservative determination of the temperature of the hottest star. We declared that the most massive star was about 150 times the mass of the sun, which is still an amazingly heavy star, but it's pretty. It's not as extreme as 2,000 times the mass of the sun, but it's still pretty
Yeah,
amazing.
yeah, that's still pretty extreme. A star like that is going to. I was just trying to quickly do the back of the envelope on how long such a beast might live, and that's a really short lifetime given what its luminosity must be.
And there's since our study, Paul Carruthers analyzed some spectra, some other spectra other than ours, and he determined that it was actually hotter than what we had determined, and that increased the mass by a factor of 2-ish. So it could be as massive as 300 times the mass.
That's amazing. As somebody who studies stars like the sun, which is of course one solar mass, I was smiling at your last slide where you're characterizing sort of 6 solar masses as intermediate, because for me that's huge.
Yeah, right. And so then the other interesting thing was we said, well, okay, we have this function that describes the number of stars as a function of the mass of the star. And at what point does this function say there's one star? And in fact, it's 150 solar masses. So that sort of all hangs together.
Yeah, and I think that's important to point out for everyone that because of the way the initial mass function works, O stars just in general are incredibly rare. They're very important because of their brightness and their luminosity, but there's almost none of them, and you found this giant clutch of them in one place.
Yeah.
It's remarkable.
Yeah, it was really cool. It was a very satisfying piece of science.
So, yeah, absolutely. It's fun to explore these sort of extreme ends of the parameter space because they tell us a lot about the universe. Now, Jim Davies has a question. Given how clustered together these stars are, so the first supernova that goes off, would it or how does it potentially affect the other stars around it?
I think so. One of the things we did was one of the people on the WIFPIC team was concerned about mergers of stars. And so my recollection is that when we actually looked at it, even though there are lots of stars in a small space, relatively speaking, the stars are still pretty far apart.
Yeah.
There's still a lot of space in between the stars. So I don't know the answer to the question of what happens when they all start going supernova. How do they interact with each other? I don't know the answer to that. Mm-hmm. But it's not quite as they're not rubbing shoulders yet.
Yeah, it's sort of like we hear a lot about galactic collisions, but the galaxies may pass through one another, but the stars are so far apart, they don't run into each other. Yeah, right. So another question, is there an explanation for why so many O stars in this one region, given that they're so rare? Is this just one of those unusually huge molecular clouds that they all formed from? Or?
Yes, exactly. I mean, so first of all, this is a huge cluster. The cluster... So I didn't really talk about the cluster, but the total mass in stars in the cluster is probably something like 500,000 times the mass of the sun. There are these objects called globular clusters that in the Milky Way. These are globular clusters that contain 1 million times the mass of the sun, and all of the globular clusters are very old. They formed in the first few billion years of the lifetime of the Milky Way. Because the conditions then were just right for forming those kinds of clusters. And so if you have and we'll come back to what is needed to make those kinds of conditions, but if you have those kinds of conditions and you have this huge cloud that forms this huge mass of stars, just because of this proportionality, this what's called the initial mass function, you're going to form lots of massive stars, but then tons and tons of low mass stars too. So you're going to populate the whole range in masses, and it's just because it's a big city in the star forming realm that there are lots of massive stars there.
Yeah.
Now what?
Oh, go ahead. Sorry.
Well, then what does it take to make a cloud like that? And people have speculated, so 30 Doradus as a whole is a huge star-forming region. What did it take to make that star-forming region? Some people, when you have a large one of the things that will happen is when you have a large concentration of massive stars that form in one space, and then they explode a supernova, they blow a hole in the gas in the galaxy. And some people have argued that there's a shell. So when you blow a hole, you make a shell around the hole. So there were two shells that intersected and collided, and that produced a huge cloud there. Then there are things. There's another up above 30 Doradus. There is a huge hole where 15 million years ago a large concentration of stars formed. It's called Constellation 3. It has a hole in the gas and a rim around it, and people have argued that may have been due to the Large Magellanic Cloud moving through material and causing ram pressure stripping and ram pressure stuff and stuff like that.
Yeah.
So you can form a huge cloud. So there are ways that you can force gas together into a huge cloud.
Yeah. And I think this is actually a really important point, to point out that really rare things happen. They don't happen very often, but they do happen. And so it may as well be in the LMC as anywhere else. And, that applies to real life too. When we're at such time as we're all able to take vacations again, somebody is going to go somewhere overseas and end up in the hotel right next to a college roommate. And what's the chance of that? Well, really low, but, rare things happen. And it's not magic or remarkable. It's just the natural way that things work. So Stargazer 45 would like to hear a little bit about the magnitudes of maybe the nebula, the stars. Can they be observed in a small telescope, or do you pretty much need Hubble to see them?
Let's see, can I go back here? You can just use your eye. You have to be Chile, but you don't need a telescope. You don't need binoculars. You just need to go out and look. Here's the Large Magellanic Cloud, and here's 30 Doradus right here.
Yep.
So
now, you have to be in Chile. You can't be in the U.S.
Yeah, you have to be in Chile. You can't see you can't distinguish R136 out of this in this little nebulosity. You don't have the angular resolution for that.
But about 4 years ago, we took a group of some of our more generous Lowell donors down to Chile for a trip, and we actually had an evening at a public observatory and got to look at the Tarantula Nebula through a 24-inch telescope, and it was easily the most spectacular. Just the size of it, filling this large field eyepiece. It was just a magnificent sight. So Albert Smith would like to know if there's any evidence that some of these massive stars have binary companions.
Not that I know of. You would see if you we took spectra, and you would see the lines from the different companions, and you'd see them move as the companions orbit around the center of mass. To my knowledge, nobody has ever done that or followed a star for a period of time and to see if things change. But I don't think we saw any evidence for it.
Okay.
That doesn't mean that they aren't, but.
All right, well, we're coming up towards the end of our 45-minute period here. I thought I'd ask Deidre just one more question that might be of interest to the viewers. You talked about making these observations with HST, and you mentioned a proposal, and that process might be of interest. I mean, you don't just casually call up the STSCI and tell them you're coming to observe. There's a process, and it's actually very difficult to get time on the HST.
It is. I don't know what the oversubscription rate is these days, but it's high enough that most proposals are turned down. So what you have to do is there's a call for proposals, and you have a deadline by which you have to put together a proposal, and you have to submit it along with. So you write an essay, usually 3 pages or something like that. And you write an essay explaining what you want to do, why you want to do it, and why it is so important that your peers, other astronomers, think that you should be given the telescope time when other people are turned down. And so then in your proposal, you also detailed exactly the instrumentation specs of what you want to do and how you're going to do it. And then the proposals are sent to a panel of reviewers. These are other astronomers who agree to spend their time reading proposals and ranking them. And they rank them, and those that are at the top are awarded telescope time. And in the past, the oversubscription used to be a factor of 10. I don't know if it's still that today, but if it's an oversubscription, a factor of 10, 90% of the proposals are turned down. And so that's very, very discouraging. But
it is, and very competitive. So maybe the moral for our younger viewers is, if you remember when your teacher assigns you those irritating 3-page essays to write, there's actually a reason you need to be good at that. We do have one more question that came in, and then I'm going to wrap up and tell you a little bit about next week's episode. This is a question that came in from Bob Filler. He writes, Deidre described a sequence of frequently focusing on a single star, then changing the direction to a star cluster. Does that procedure put a significant energy or fuel demand on HST?
I don't think it's significant in that, I mean, it has these gyros that help it point, and I don't know the details of all that, but you're moving, so the telescope is constantly moving from one object to another because not everybody's observing the same thing, right? So it goes here and it does one person's project, and it goes here and it does another person's project. So in this case, you had to go to a star that was very close to R136 but isolated. And so then you would just center up there, and then you'd offset. So the offsets were a tiny distance compared to going from R136, say, to somebody else's favorite quasar.
Okay. All right. Well, thanks a lot, Deidre. This has really been a great conversation. Since I do smaller stars, it's fun to sort of talk about these monsters from time to time, especially as unique a region as this. So everyone, if you've enjoyed today's broadcast, you can support Lowell Observatory by becoming a member and subscribing to our YouTube channel. Next Thursday, we will be back with cup number 5 of Cosmic Coffee. My guest for that will be the director of the International Dark Sky Association, Ruskin Hartley. And sort of in concert with International Dark Sky Week and Earth Day, we're going to be talking about dark skies and light pollution and how to preserve some of these or all of these magnificent sites such as Deidre's been discussing today. So thanks for joining us. Thanks, Deidre. That was really a great presentation, and really appreciate your time and coming on the